This lesson deals with MOSFET inverters. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 38. Suppose we take an NMOS transistor and hook up a resistor and a power supply and do our basic inverter like we did for the BJT. What's shown below is a set of VI characteristics of a MOSFET with a threshold voltage of 2 volts. I'm going to draw a load line like we did for the BJT. So if I were to short these terminals, the current that would be flowing in here would be 10 volts divided by 10K, and that's 1 milliamp. That's right here. And that this is an open circuit, no current flows, and the voltage here would be equal to 10 volts. Connecting those two up, we get a straight line, and the intersection with these VI characteristics will give us the solution. Suppose that our input is a square wave going between 10 volts and 0, so logical 1, logical 0. We apply 10 volts for the input voltage. That's also the gate source voltage. Here's the line where the gate source is equal to 10, 9, 8, so on, all the way down to 2. The voltage here is approximately 0.57 volts, and the current just a little bit less than 1 milliamp, 0.94 milliamps. My voltage is about 0.57, and my current is about 0.94 milliamps. If the input goes to 0, then the gate source voltage is 0. Anything less than 2 is just on this line, and we intersect the load line right here, and so the output voltage is going to be equal to 10 volts, and the current will be 0 because we're not drawing any current when we're in cutoff. How much power is absorbed by the logic gate? Well, it's the integral over a period divided by the period of the product of the voltage of the power supply times the current coming out of the power supply. That's what's being supplied, and that's what will be absorbed by our circuit. VDD is a constant, so you can pull that out in front. We're left with the average value of the current I sub D, which we have here as just a square wave. Here the area is 0, and here the area is just the height times the width. It's 0.94 milliamps times T1. Then we're going to multiply that by VDD divided by T. This will predict the power consumed by our logic gate. As T decreases, in other words, as the frequency goes up, the power goes up. If we were to lower the resistance, that would make this value here get larger. The value here was approximately the power supply divided by the resistor. Decreasing the resistance would increase the power. Increasing the frequency would increase the power consumed. Every integrated circuit has some capacitance, or also if we hook up a load, there'll always be some capacitance across it. One of the problems with logic gates is dealing with capacitive loads. If we apply 10 volts here, the output is going to be very low. Let's just say it's approximately 0 volts. It's actually around 0.57 from our previous page. Then if we put 0 volts here, we're going to cut off the transistor because the threshold is 2 volts. Applying 0 volts, we cut off the transistor. We just have an RC charging circuit. The output voltage is some first-order differential equation with a solution of A plus B times e to the minus t over tau, where tau is the Thevenin resistance times the capacitance, and that's R sub D times C sub L. Let's assume that the initial condition is 0, though it's about 0.57, and then plugging in t equals 0 here, we'd have that A plus B is equal to 0. As t approaches infinity, it becomes an open circuit, and this voltage approaches the power supply. It's equal to VDD. But plugging in t approaching infinity makes this term go to 0. We just have A plus B times 0, or just A. Our solution then is some VDD, that's my value of A, and B is the negative of A, times e to the minus t over tau. We have a simple RC charging circuit that we've seen before in this course at an ECE302 and 201. It takes about 5 time constants to get to steady state. Now suppose that R sub D were 10K and C sub L were 10 picofarads. Then our time constant would be 0.1 microsecond. If we go back to page 38, we do have an initial condition of 0.57, and we will eventually get to 10 volts. But the 5 time constants means it's going to take 0.5 microseconds added to whenever this instant in time occurs. We have to wait for the output to get to a level before we can start to switch again. If we lower R sub D, we'll speed up the response of our circuit, but we'll also then increase the power consumption. What we need is an element that has 2 values of resistance. One that's low for fast switching, and one that's high for low power consumption. It's possible to do this with a transistor. What's shown below is a CMOS inverter. CMOS is short for a complementary symmetry metal oxide semiconductor, just CMOS for short. This uses both NMOS and PMOS transistors, and here's the configuration for an inverter. Here's an N-channel MOSFET, and here's a P-channel MOSFET. I'm going to connect the bulk of the N-channel to ground and of the P-channel to the positive power supply. I'll explain in a future video why we need to do that. What this is doing, because we're going to be operating these transistors in either ohmic or cutoff, is that this looks like a resistance, and likewise so does this. I'll call this my resistance from source to drain of the P-channel device, and my resistance from the drain to source of the N device. I analyzed this circuit symbolically, but let me put some numbers on it. It might be a little bit easier to follow. Suppose that the threshold voltage is equal to 1 volt, just to make the numbers easy. And I use a 5 volt power supply. And I'm going to apply a voltage here that's either 5 volts or 0. So suppose I put 5 volts here. Then the source to gate voltage is going to be 5 volts minus 5 volts or 0. This is cut off. That makes this an open circuit. But in reality, it has some resistance. Let me just put a value on it of, say, 1 gigaohm. That's a big resistor. The gate source voltage here is going to be this node voltage minus 0, which is 5 volts. And 5 volts is greater than threshold. So we could be in current saturation or in ohmic. Let me assume it's ohmic, and then I'll verify that. But if it's a logic gate, it's going to be switching between high resistances and low resistances. This is really a very low resistance. It's technically not 0. Let me put a value maybe of 1 ohm here, just to make numbers kind of easy to work with. So what's the output voltage? It's going to be 5 volts times 1 ohm over 10 to the 9th plus 1. It'd be about 5 nanovolts. Compared to 5 volts, that looks like 0. So that's roughly 0. A high input gives me a low output. I need to check that the gate to drain is the correct inequality. Let's find that. So here's the gate to drain for the N-channel device. So what's the voltage between here and here? Here's 5 volts, and then here is basically 0 volts. 5 volts across the gate to drain of the N-channel device. So that is our conditions to be in ohmic. Now what about the drain to gate voltage for the P-channel device? Well, this node voltage is 0 and this node voltage is 5, so it's minus 5. And minus 5 is less than 1. This is in cutoff. Let's take a look at the next case where we're going to take the input and make it low and then find out what the output is. For me to do that, let me erase all this stuff here. On the next page are the words describing how this works when you put 0 volts here. What's the gate to source voltage here? It's equal to 0 volts. And if threshold is 1 volt, then this is cut off. That would make this resistance a big resistor. Again, I'll put 1 gigaohm here. And now what's the source to gate voltage for the P-channel device? Well, it's 5 volts minus 0 or 5 volts. That's greater than threshold. So this is either in current saturation or in ohmic. Let's assume it's an ohmic because it's a switching circuit. And so it's going to be a low resistance. Let's again put maybe 1 ohm here. What's the output voltage? It's 5 volts times 1 gigaohm over 1 gigaohm plus 1, and that's 4.99999, about 5 volts. The input's low, the output's high. Need to check that the gate to drain is the right inequality. So here's 0 volts, and here is 5 volts, so this is minus 5. That is cut off, and then we're going to find the drain to gate voltage here, which is going to be 5 volts minus 0, so it's going to be 5 volts, so that's greater than threshold. That is in the ohmic region. What about the currents flowing in our circuit? I forgot to calculate it in the last one, but we had a total resistance seen by the power supply in the previous case of 1 gigaohm and 1 ohm. And we have the same thing here. We now have 1 ohm and 1 gigaohm. The current that's coming in both cases for a 5 volt input or a 0 volt input is 5 volts divided by 10 to the 9th plus 1. And that's approximately 5 nanoamps. This logic gate is consuming 5 times this, or 25 nanowatts of power. That's unbelievable. All logic gates before this always consumed power when they were in an operating state. There is, however, some power consumption occurred when we switched between these states. We'll take a look at that next. Here's what we just did. Now I'm going to run a SPICE simulation, but I really need a much more accurate model than what I've been using. So when I grabbed what's called a level 2 model off the web, it was from a company called Orbit Semiconductor that was doing a 2 micron double poly double metal end-well process. Level 2 model has to do more with fabrication parameters. This is going to allow us to get a pretty accurate simulation. Now there are many more levels in modeling. This is called a level 2 model, but the levels go up quite high actually. So as they begin to find out more about the equations of the MOSFET, they begin to improve the modeling and actually add it into the SPICE program. So if you look at the previous page, I had an input between nodes 1 and 0. Power supply was at node 2 to ground, so it would make that 5 volts. And my P-channel device is between the drain, gate, source, and bulk. The drain was 3, the gate was 1, the source was 2, and the bulk was 2. For the N-channel device, again, we have drain, gate, source, and bulk. The drain was 3, the gate was 1, the source was ground, and the bulk was also grounded. I'm going to sweep the voltage from 0 to 5 volts. I'm going to do 2,000 data points. Dividing 5 by 2,000, I get 2.5 millivolts per step. There's a lot of interesting things that are happening with very small changes in voltage. Take a look at the output on the next page. What's plotted here is the output voltage, node 3, versus the swept input, which was where Vin was. If you recall, when the input was low, the output was high. When the input was high, the output was low. So we're seeing the same behavior, but now we're seeing all the points in between. I've also plotted below this the source to gate and the drain to gate for the P-channel device, and the gate to source and the gate to drain for the N-channel device. I've also included the threshold voltage, marked here in red. If you look on the previous page, the threshold voltage for the P-channel device is a minus 0.8889, but with our notation, I'm using the negative of that. It's going to be 0.8889, in other words, a positive value. And the value for the N-channel device was 0.8756. When I'm looking at an input of 0, I see that the source to gate and the drain to gate are both greater than threshold. And that means that the P-channel device is in the ohmic region. And here I have the gate to source and the gate to drain less than threshold, which would mean that it's in cutoff. And that's exactly what we saw when we did our hand calculations, and also what you see right here. That's what makes the output high. And of course, the current that's coming in is very, very small. Let's look at the other extreme end here, where we've got a 5 volt input. Now I have the source to gate and the drain to gate less than threshold. That would put the P-channel device in cutoff. And I have the gate to source and the gate to drain for the N-channel device greater than threshold. That puts it in ohmic. What happens in between? This region over here, I see that the source to gate and the drain to gate are still greater than threshold. We are in ohmic, but the N-channel device has the gate source greater than threshold and the gate to drain less than threshold. So that makes it in the current saturation region. Now this transistor has gone active and the current is going to start to increase. A similar thing happens over here. In this region, I have the gate to source and the gate to drain both greater than threshold. So that puts me still in ohmic as it was here. But for the P-channel device, I have the source to gate greater than threshold and the drain to gate less than threshold. So that puts it into current saturation. Now what happens in between here is a little tricky to see. But when you're operating in this region here, the source to gate is greater than threshold and the drain to gate is less than threshold. That puts it into the saturation region. And the same is going on over here. And when I'm operating over here, the gate to source is greater than threshold and the gate to drain is less than threshold. So they're both active at that point or in the current saturation region. That actually will get the most amount of current flowing. There is current between the switching of the states. Now we can't just go from 0 to 5 volts instantaneously because we have straight capacitance and lead inductance and nothing can jump instantaneously. Let's take a look at the next page and see what the current levels are coming out of our power supply. I'm plotting the current that's coming out of the power supply. Now in SPICE, current enters the plus terminal, so I want current to come out of that plus terminal. So I'll take the negative of the current of the power supply. You can see here when the input is low, the current is low, and when the input is high, the current is low. But as we switch between those states, and eventually both transistors go active, we do get a peak of current. We're consuming power when we're away from the two extremes. I did a little sketch here. When the input goes from 5 to 0, the output goes from 0 to 5. And it's in this transition of falling down that we cause the output to go from 0 to 5, and that gives us a spike of current of about 23 microamps maximum. Now, this all repeats again once the input goes back up again, but that's part of another cycle. So in this cycle over here, we only consume current for a very short instant in time. And our power absorbed is the voltage times the current of the power supply on the average. Pull this out, and now we've got the average value of the current, which is very small. If you start to increase the frequency of your clock, which is what runs the computer, which runs your smartphone, which runs microcontrollers, we're going to see the power consumption go up because we're having many more of these cycles per second. That's why your phone gets hotter, your laptop gets hotter, the higher the frequency it runs. There are some microcontrollers that actually allow you to pick the frequency to optimize power consumption. And these are MOSFET inverters.